All right. Hello, everyone. My name is Tyler Miraglia. This is my lab video for Module 7. This is my second attempt at recording. I just spent a while on the first recording and then realized afterwards that it was all in the wrong format that I can't upload. So we're going to try again. I want to start by saying I had to take a little bit of a different approach to this lab as was laid out. The thermistors that were required for the course were on back order when I tried to order everything. So I ended up ordering these off Amazon. These are from GeekFun. They are NTC MF58 3950B glass 10,000 ohm thermistors. We'll see later that they didn't have all the information that was needed, but there was a workaround for that. There's other ways to calculate the resistance of a thermistor that I went into. So here are two circuits that I ended up building. This one on the left was what I used to calculate the resistance of the thermistor, since I didn't have all the information I needed. We'll get to the equation, I think, in one of the next slides. It'll make this make a little more sense. What I have here is a 5-volt DC input going straight to one end of the thermistor and then taking a voltage reading at the other end of the thermistor with a 10,000 ohm resistor connected to ground in between. And over here is the circuit I used for the LED to light between 70 and 100 degrees Celsius. That was a simple 5-volt direct current or digital input, the LED, and a 330 ohm resistor then connected to ground. Here's the front face. I tried to keep it as similar as I could to what the lab required. Got the stop button, the temperature in Kelvin, the temperature in Celsius, and then this waveform chart, which I should have renamed and renamed the axes, but not that huge. We'll see how it works. And over here I have the input voltage and output voltage for that circuit that I showed before. Okay, now because I didn't have all of the same variables as the equation called for, like I didn't have A, B, C, D, they weren't on the data sheet for the thermistor. All they gave me was beta, which was 3950, and the initial temperature that it was rated for be 75 Celsius or 298 or 25 Celsius, 298.15 Kelvin. And at that temperature, it's rated at 10,000 ohms, which was the resistance baseline. And to calculate the actual resistance, we use this equation here, which is resistance equals the baseline resistance times the input voltage divided by the output voltage minus 1. We go back. We have an input voltage here. And we can get the actual resistance by using that equation and we're taking the output voltage after the thermistor. And that all gets input through here. I used the analog inputs on the myDAQ, the DAQ assistant, to get the input and output voltage. Input voltage was the first, so I put that to input 0, which is why I have the 0 here. Output was input 1. 1's there. The index, the arrays, and then I have it set to go to the indicators on the front face, so the input voltage here and output here. I have a picture of the physical circuit later. We can go over that. So once we calculate the resistance of the thermistor, this top equation should actually be 1 over T equals 1 over the initial temperature plus 1 over beta times the natural log of the actual resistance over the baseline resistance. So to simplify this, we calculate the natural log of the actual resistance over the baseline resistance before and get R. So we take the actual resistance, divide it by baseline resistance, which is 10,000, and take the natural log of that. And you'll notice I said the equation before was 1 over T, but using the formula blocks here, 1 over T wasn't working, so I just, flipped it around. So it was T equals 1 over the whole other side of the equation, and it gave us pretty good results. So the output's going to be in Kelvin. That's going to go straight to the indicator on the face, and then minus 273.15, and that'll give us the temperature in Celsius, which is sent to the indicator on the face again and the waveform chart on the face. Also, we're going to send that up here to a comparison function block, which is I think this was called is in between and coerce. We weren't using the coerce function because that would change the value, so we have it set to compare. I forget exactly what it's called, but we have it so it's to the one that doesn't coerce. And here we have the maximum value of 100 Celsius and then the minimum value of 70 Celsius. And this bottom node is going to be a true or false Boolean output. Now, to control the LED, I have a digital output set up with a DAQ assistant. And the digital output, the data input has to be a true or false one-dimensional Boolean array. And for whatever reason, the true or false Boolean, maybe it's because it's not an array. So I ended up converting it to a number, then converting the number to an array. This first function here is convert to number, or Boolean to number, and then number to array, and then reformat or rearrange array. And this one is just making it a one-dimensional array. And then that is accepted by the DAQ assistant. So it's a one-dimensional true-false array, pretty much. All right, here's the physical circuits. You can see the thermistor here is connected to 5-volt input. So it's always getting 5 volts. Well, roughly, as we see here, is about 4.7. But that's why we needed to know the input and not just give it, 5 volts, because then it just gives it a little more accuracy. And the 10K resistor here connected to ground. I know all these wires are kind of hard to follow, but the black and green all go to ground. This red one goes to the positive analog input 0. The yellow one goes to positive analog input 1, which is reading the output voltage, and the red one's reading the input voltage. And then this white one is the digital output to run the LED that is looking for the true or false Boolean. Whoops. Got a little click happy. And then over here we just have the LED 330 ohm resistor connected to ground, and then our 3 ground wires. Obviously this setup isn't going to work to get a thermistor into a pot of water that's boiling. I mean, I guess I could have stuck it in there, but it's just not a very good idea, I guess. So this is what I ended up doing. I took, I think it was 6 jumper wires, 3 on each side, connected them, gave me about 2 feet of length total. These leads on the thermistor were not thick enough to fit in the female leads on the wires. So I stripped the end of the wires, curled them up, twisted them together, tied them up as best I could, keep the best connection there. That way, um, you know, it wouldn't give a false reading because of resistance from not making a good connection or anything. Here's the video. I'm gonna pause it real quick. So initially, at this point in time, I had just placed it in the water, placed the thermistor in the water. It was at room temperature before. Might have been a little hot because I might have touched it picking it up. So around 28 Celsius. It was around 20. Still reading kind of high for what I expected and what I had tested before. And then as soon as I put it into the water, it jumped up to 40 Celsius, which didn't really seem right to me. 40 Celsius is 104 Fahrenheit, and the water was tap cold. I didn't have any ice, but it definitely wasn't hot water. For whatever reason, as soon as I put it in, it jumped up to 40. We'll see. It kind of comes down a little bit as the water heats up, stays around in the 30s, and then starts to climb back up. So I do have an electric stove, which may have given me some weird results here. As we'll see, it's climbing now. I tried to keep the circuit in frame as best I could, but it was kind of hard. I wanted to make sure you could see the water when it was boiling. And this video sped up 10 times, so it's about 10 times faster than actual time. We'll see in a minute here. It's still going up. Not very linear. Kind of jumps around a lot. Which in my research I've seen that thermistors can be that way sometimes. So it wasn't too far from what I expected. Now we're just over 70. So we can see our lights on. Water's boiling. I pulled it out just to make sure because it kind of staggered, came stagnant around 70. So I pulled it out, put it back in, let it cool down. You can see when I first pulled it out, it dropped to 40. I put it back in, went right back up to 70. And then I pulled it out again, let it sit out. It dropped down to just over 15 Celsius, which my assumption from that is the water evaporating kind of made it colder. So, you know, evaporation will pull heat energy away. Which is why you get cold when you're wet and drying off, air drying, I guess. And then I put it back in, jumped right back up to 70. But I mean, the water is clearly boiling. I would expect that to be around 100 degrees Celsius. But 70 was about the highest I got. I'm not sure if maybe I had broken the thermistor because I did keep a flame near it just to make sure it was working earlier, and you know, not watching two things at once. I potentially could have overheated it because I think it's only rated to 350 Celsius, but a torch flame can get pretty hot. I don't know the exact temperature, but I think I saw the charts spike up to really hot. So I don't know if maybe I had broken it, and that's why I was giving weird readings. Because I mean, even after I let it cool down for quite a while, and it's stayed around 60, I pulled it out after, let it dry off, and even when I restarted it, it stayed around 60 Celsius. When this is what I got with a brand new thermistor. Was just it was around 21 Celsius, which makes sense to me. I mean, I do live in New England, so it's a little cold. 21 Celsius is about 70, which even that seems a little bit high for what it was in my house. It did feel a little cold. About 70 Fahrenheit, I should say. But yeah, other than that, I think unless some of the values from like the nominal values here, because it's 10,000 ohms plus or minus 5%, and then if that was on one side and our thermistor was on the other side of its tolerance, then we could see a couple degrees difference probably. But yeah, overall, I say I this was a kind of interesting lab for me, especially since I didn't have all the proper information to get it done as was laid out, but it didn't take much research to figure out different ways to calculate what I needed, and pretty much everything else was just trial and error. I mean, a lot of the myDAQ stuff or LabVIEW stuff was similar to what we've done in the past, and it's LabVIEW's error tools are very helpful because that's what made me figure out. Go back to the LabVIEW screen. Or over here that I needed to convert to a one-dimensional Boolean array, because when it wasn't that, it would give me an error, and then I tried to run it, and I to get that error message, and it would tell me exactly, oh, you're outputting this, but you need this. Okay, so how do I get from that to that? Do a little research, mess around with some of the functions, eventually got what I needed, and it worked exactly as I needed to. So yeah, this was interesting. I hope you guys learned something from it, because I know I definitely did. And hope you guys enjoyed. Thanks.